大家好，我是清华大学电机系黄眼介。今天我要介绍圆柱状的波导。之前我们介绍的这个矩形的波导，显然形状不太一样，我们描述的方式也会不太一样，但是其中的物理很多都是类似。那所以呢，我会从这个basic concept 开始做一个介绍，也就是提供各位一些物理的图像，了解这其中的差别。然后呢，我们必须学一点新的数学来描述这个新的结构。那这个新的数学呢，里头主要是有关 Bessel function 的一些特征。然后跟之前一样，我们会把这个波导里头的模态呢，分成 Tm-mol 跟 Te-mol 来描述。最后一些这个单元的回顾。So the first session is about basic concept. So let me show you on the first slide a rectangular waveguide given by this cartoon. And previously, you already know that the field is going to bounce back and forth between these two boundaries. But the wave still travel along the axis. So along the axial direction, you will have a traveling wave. But along the transverse direction, you will have a standing wave like this. And this is the standing wave pattern you will expect from this rectangular waveguide. But when you compare with the field pattern inside a cylindrical waveguide, the field pattern will be slightly different, but the physics is very much similar. For example, in the rectangular waveguide, the field pattern appears to be uniform across the transverse direction. You will be expecting the field amplitude at this point similar to the field amplitude at this point and also this point, because this is the flat boundary. But when you look into a cylindrical waveguide, the story will be different because the field will be concentrated on the axis. So this means that in this standing wave pattern, you will have higher field at the center compared with the field close to the circular boundary. So this is the first difference between a cylindrical waveguide and a rectangular waveguide. Other than that, you are still expecting a traveling wave along the axial direction. So if I just plot a cylindrical waveguide here, suppose it's a metallic boundary. So all the field will be confined into this cylindrical region. And if you write down the field inside this waveguide, you'll be expecting the field will be depending on the radial coordinate and also the angular coordinate r and phi, and this field will be propagating along z direction. But sometimes you will have the constructed interference on the axis. Therefore, you will see a high field right on the axis. But sometimes you could have destructive interference at the center of the axis. Therefore, you have zero field on the axis. And we call this mole to be an even mole because it is an even function about the axis. And we call this R mole because this field pattern is an R function about the axis. And you can compare this field pattern with the field patterns inside a rectangular waveguide. And you see that for this even mole, which is comparable to a cosine-like field pattern inside this rectangular waveguide. For this, the R mole, the field pattern is going to be comparable to the sine-like field pattern inside this rectangular waveguide. But you have to pay attention to that on the axis for a cylindrical waveguide, the field is going to be stronger on the axis. If you compare, for example, this field strength compared with the field strength here, apparently the field strength closer to the axis is going to be stronger. But if you look into the field strength inside a rectangular waveguide along the transverse direction, the amplitude here will be the same as the amplitude here. Or if you compare this amplitude here with this amplitude, they will be the same. That is because in the rectangular waveguide, the boundary is the surface is a flat surface. So you don't concentrate field on the axis, But for a cylindrical waveguide, you'll be expecting that the field is going to be stronger near the axis due to the focusing effect from the cylindrical boundary. So now let me turn to a little bit just broaden the situation that we don't confine ourselves to a metallic boundary. We allow this material to be, for example, a dielectric material, just like an optical fiber. So possibly you could have standing wave inside this region, but then you could have the wave leaking outside. If the wave is fully guided inside, then you could have evanescent wave outside this cylindrical region. And sometimes you have leaky wave going out from this cylindrical area. So you could have the radiation wave along the radial direction described by this radiation field where you see this propagation constant along R direction. And sometimes you have a surface wave. So the field could be concentrated on the surface of this waveguide. And inside this waveguide, outside this waveguide, you have evanescent wave. So we'll be discussing all the possible solutions in the cylindrical system so that we can pick up the right solutions when we are given a problem. Now we talk about the analysis for a TM mole inside this cylindrical waveguide. By definition, if you have a TM mole inside a waveguide, you'll be expecting an electric field along the axial direction. And in this case, the electric field is going to be along z direction. And so you write down Ez as a function of R phi z, but you know that the field will be propagating along z direction. So you put exponential minus gamma z here. And along the transverse direction, the field profile is going to be described by this factor as a function of R and phi. So you put this expression into Helmholtz equation. And don't forget that in this Helmholtz equation, H is the eigenvalue which is going to give you the cutoff frequency of the waveguide. Very similar to the discussion we have for the rectangular waveguide. Specifically, H squared is going to be equal to gamma squared plus K squared. And don't forget that the K squared is the where K is the frequency, angular frequency, multiplying with the square root of mu epsilon. So once you put this expression into Helmholtz equation, then we use the technique called separation of variable to solve the problem. Well, you just write down this Ez as a multiplication of R as a function of R and phi as a function of phi, and then put it into this expression. Then you separate this expression into two independent expressions connected through this n square. And so if we look at this expression, that gives you the solution for the field depend on the phi, then you can easily solve this ordinary differential equation given this n squared here. So n is a mole number along phi direction. And in fact, you have known this solution of this expression from the lecture 10 in electromagnetic 1. And if you still remember, we look into this expression when we try to solve the electric potential problem based on Laplace equation. So we just pick up the solution from lecture 10 of electromagnetic 1. And the solution look like this, which is the superposition of a cosine function and a sine function. And you know that for full circle problem, there's always a periodicity of 2 pi. So this n has to be an integer for such a full circle problem, because the whatever field you have, say at this point, if you rotate 2 pi back to the original position, then the field is going to be the same. But I want to point out to you that it really doesn't matter for you to write down a superposition of sine and cosine, or just write down a solution with sine or cosine, because the sine and cosine are different by a phase shift of 90 degrees. So if you choose the solution of cosine, you can always redefine your coordinate by rotating the reference line by 90 degrees to create another solution of sine. So to simplify the discussion, for what follows, we'll just pick up the solution of cosine and write down this function as a coefficient multiplying with cosine n phi. And this n, again, is an integer if you deal with a full circle problem. On the other hand, if you have to deal with the partial circle problem, you need to be careful that the fundamental period of the problem is not going to be 2 pi. It could be a fraction of pi. So this means that this n could be a fractional number. And this n should be replaced by another coefficient like a nu, which could be a fractional number. It's not necessary to be an integer. So be careful about some problem that only require you to look into the field pattern with a fractional circle, but not a full circle. 所以呢，在这个小节里头，我介绍了一些基本的概念。这基本的概念呢，就是先比较这个矩形的波导跟圆柱状的波导，它的基本的不同会在哪里？它们的物理很像，但是场形会不一样，因为几何形状已经不一样了。所以呢，在一个这个cylindrical waveguide 里头呢，同样的你会找到一个 traveling wave 呢是在轴向在跑。但是在横向上头同样是一个这个驻波的形态。那但是呢，因为它的这个边界是一个圆形的结构，所以它的场呢在中间的部分会比较强，这个跟矩形波导不太一样。那在一个这个圆柱的这个系统里头呢，如果有场跑到这个圆柱外头的话，这个场这个波可以是辐射的波，也可以是消散波。如果说这个波是在这个圆柱的结构里头呢，是这个 well guided 的话，那外头的话就会是一个消散波。但是 if you have a leakage field from the waveguide, then the wave outside the cylindrical system could be a radiation wave. 然后呢，对一个这个整个是圆的对称的一个圆柱波导来讲的话呢，在 phi 的方向上的解呢，是用这么一个cosine n phi 的这个式子来描述。因为呢，在一个完全是圆整个圆的结构里头，它的周期角度的周期呢一定是2拍，所以呢这个 n 一定是一个整数的值在那个地方。但是如果有些问题，这个波导的这个横截面它不是一个完整的圆的话呢，这个 n 有可能是一个这个 fractional number， 也就是一个分数在那个地方，所以必须慎重的选择这个mole number n 来解一个问题。那这是这个小节的一些重点。